Okay, let's talk about the kinetics of running. And I've drawn a stick figure, not a great stick figure, of somebody running. Time 1 represents the moment before the person strikes the ground. Time 2 represents striking the ground. Time 3, the person lowers themselves as the lowest point. That's a little extreme. The knee goes through flexion, the hip goes through flexion, the ankle goes through dorsiflexion, and then the person starts to propel themselves upwards. So this is a later portion of a stance, and then eventually the person takes off for the next stride. Okay, so this is flight. This is contact. And this whole period here, we would call stance phase, where the foot is in contact with the ground. Foot in contact with ground, and obviously that's the part that I'm going to be interested in. And then on the ends of that would be flight phase, flight and flight over here, flight phase, where the person is not in contact with the ground. And for running, there's a period where neither foot is in contact with the ground. During walking, there's one of the feet is always in contact with the ground. All right. And truthfully, sometimes in running, we actually do have a period where both feet are in contact with the ground, like if you're running really slowly. And anytime we have 2 feet in contact with the ground during locomotion, we call that double support. But running, we typically define as having no double support. But that gets a little limited when we start running slow. And so a better way to define running is the center of mass is at its lowest point at mid-stance. Okay, the center mass is at its lowest point, and prior to and after that point, center mass is higher. During walking, center mass is actually at the highest point at mid-stance. All right, but right now we're going to be doing walking. So we have this general, if we track the center of mass, remember that's what we're interested in with our kinetic analysis, the center of mass will go down, and then it will start going upwards. So we have this progression of downward movement and then upward movement, which each dot representing a different frame in a kinematic picture of the center mass during a stance phase. Okay, so forces acting on the runner are body weight, gravity, and ground reaction force. So I'll just take one picture. We have the ground reaction force right here, pushing upwards on the person, and body weight pulling down on the person. That's it. Those are the 2 forces. That's negative. That's negative because it's downwards. And we put those forces into the equation, MACOM. Those 2 forces add up to mass times acceleration. So now let's try to understand what the ground reaction force will look like if we can model the acceleration of the center mass. Okay, knowing the basic kinematics, we should be able to do that. So let's bring out our worksheet, and we do running. And I'm only going to focus on the vertical dimension right now. Remember, up is positive. And we are working towards understanding our ground reaction force down here in newtons. All right, so let's draw this out. Here's contact. So I'll put GC for ground contact. That's a typical way that we refer to this. And the way I did my stick figure, I drew the stick figure hitting the ground with the heel first, but it could be the toe, it could be the lateral aspect of the foot, it could be anything. So a more general term is ground contact. And then over here, we have takeoff or toe off, either way. Takeoff. We have flight over here. And in this period, this whole period is going to be stance. Now, if I'm starting to talk about a stride, I'll start pulling in, stride is, right side to right side, right contact to right contact, left contact to left contact, that's a stride. And I would break the stride into a stance phase and then a swing phase. But right now I'm just going to put flight for now. And that indicates no double support, no contact with the ground, and you'll see why I did that. All right, so prior to ground contact and after contact will be indicated by these lines. Prior to contact, the person is a projectile. No contact with the ground, no other forces acting on the person. The person strikes the ground and the center mass is that high. The center mass goes down and then back up into the next flight phase. Prior to and after contact, we have a projectile situation. And what's nice about that is we know the kinematics of projectiles. This is a second order polynomial. We know velocity will change at a constant rate, and that acceleration will be negative 9.8 meters per second squared. So that's good information to have. All right, let's drop down these lines. I'm going to drop down the min here. I'm going to drop down contact all the way down to all 4 plots. I'm going to drop down takeoff. Yeah, I'll drop this one down too. All right, so I have those all the way going down. So ground contact and takeoff are indicated. All these slopes are negative. Velocities will all be negative. All these slopes are positive. All these velocities will be positive. Velocity is positive after. Velocity is negative coming in to ground contact. This is the min point. Velocity will pass through 0. And I have some speeding up while moving downwards, some slowing down while moving downwards. I reach that low point, then I have speeding up, moving upwards, and then a bit of slowing down, moving upwards as well. But I'm going to be taking off at a velocity that's not 0. So velocity is some velocity here because I need to project myself off into the air in the vertical direction. And then likewise, my velocity is not 0 when I strike the ground. So I'm going to have contact with some initial negative velocity. I'm going to have takeoff, and I'm going to do the same magnitude, but just the opposite direction. All right, now I'm going to add this little detail in, and we'll come back and deal with this a little bit more. And I messed up with saying it here, but that's okay. Initially, the moment we strike the ground, we are actually still speeding up for just a short period of time after contact, and then we start to slow down, moving downwards. All right. And then, well, actually, I said it right. I just spread it out over too long of a period of time. Then we have speeding up, moving upwards. And then right before takeoff, we have a little bit of slowing down right before takeoff. After takeoff, slope is negative 9.8 meters per second squared. Prior to takeoff, slope is negative 9.8 meters per second squared. Why? Because there's neither foot in contact with the ground, and the person is a projectile. All right, so now I have these 2 new discrete events. I'm going to drop this down here. I'm going to drop this down here as well. Okay, now let's do acceleration. Negative slopes, negative acceleration, negative slopes, negative accelerations in that little region. Positive slopes, positive accelerations, positive slopes, positive acceleration, a little bit of negative acceleration right there, and negative acceleration afterwards. Now we know the acceleration before and afterwards is going to be negative 9.8 because that is flight phase. The only force acting on the person is force of gravity when neither foot is in contact with the ground. So now I have this funny region of negative forces, or excuse me, negative accelerations, positive accelerations, negative acceleration here. all of these slopes are positive. I'm going to draw a plot, and then later on you'll watch a video of a ground reaction force during running, and you'll see it's slightly different than what I'm going to draw. But that's okay. We're going to start with modeling what the ground reaction force is going to look like, and then we'll work back to try to understand some of the details of the actual ground reaction force that we calculate. So I'm going to draw what the acceleration profile of the center mass will look like based upon what I've drawn here. Something like that. I have periods of positive acceleration. I have periods of negative acceleration. Okay, I can even drop those down here to the ground reaction force plot. All right. Remember, this is all downward movement here. This is all upward movement here. Velocities are all negative in this region. Velocities are all positive in this region. Everything's downward movement here. Everything's upward movement on that right-hand side of that mid-stance. That's what the acceleration is going to look like. Remember our equation, and we derived this in a previous presentation. The ground reaction force is going to be equal to mass times the acceleration of the center mass plus the force due to gravity plus body weight. So we take every acceleration point, multiply by the mass of the person, add in body weight, and we get the ground reaction force. Prior to contact, ground reaction force is 0. After contact, ground reaction force is 0. If acceleration is negative, the ground reaction force will be less than body weight. If the acceleration is negative, the ground reaction force will be less than body weight because that product. Make sure you go watch that other presentation. If the acceleration is positive, the ground reaction force will be greater than body weight. So I'm going to go ahead and draw in the ground reaction force. It's going to follow the acceleration profile because mass and gravity are constants. And now the way I've drawn this, this dotted line represents the magnitude of ground reaction force that's equal to body weight. All right, so let's talk through this. This is time, and this is takeoff. This is ground contact. The person strikes the ground and initially is still speeding up just for a very short period of time while the person's moving downwards. But then at this moment, the person starts to slow down moving downwards. Starts to slow down moving downwards. And then at this point, the person has reached the lowest point. Center mass is at the lowest point, and movement is upwards. And we start to speed up moving upwards. Speed up moving upwards right until this point, and then ground reaction force is less than body weight, and we start to slow down moving upwards. Start to slow down moving upwards. So let's do it again right here. Speeding up, moving downwards, slowing down, moving downwards, speeding up, moving upwards, slowing down, moving upwards. And then obviously we're off into the air and we're slowing down, moving upwards there. And prior to contact, we're speeding up, moving downwards. Why is that important? Because in a little bit, we're going to watch a video of some ground reaction forces using a force platform. The force platform measures this. And we're going to get a plot that all we're going to get is this information right here. And it's important to recognize that this ground reaction force, without knowing some of these other pieces, we got to be careful how we interpret these data. This moment in time, it's a ground reaction force that's greater than body weight. You cannot fall into the trap that's saying this is upward movement, because it's not. It's downward movement. The person is slowing down, moving downwards. You hit the ground and you have to generate a lot of force, more than body weight, to stop your downward movement. But at some point you reach your lowest point, and then all the forces that you're generating are trying to speed yourself upwards, so you propel yourself off into the next stride. All right, so interpreting this plot is challenging, just like interpreting acceleration plot, because this just tells us rate of change of velocity. To understand and interpret the ground reaction force, we need to be able to get to the velocity plot still. And then we can interpret this in terms of speeding up, slowing down, and which direction movement is occurring. So when you start looking at ground reaction forces collected from the force platform, we need to be really careful how we interpret those data, because they're always going to be positive for the force platform as long as the foot is not fixed to the ground. And we need to be able to distinguish between when a person is moving upwards, when the person's moving downwards, or if we switch directions, forwards, backwards, or side to side. Right now, we're only doing vertical. Okay, so this is what our ground reaction force curve should look like. But what we're going to find is when we actually collect some data, we'll actually get this spike in ground reaction force initially. That's not shown up in my model of PVA and ground reaction force. But I could easily model that. This is still ground reaction forces that are causing a person to slow down while moving downwards. It just happens in a real short period of time, and we think that's related to why runners often get injured. And we may actually design shoes to minimize this impact force that we actually see during running. But in modeling it, where I'm just sketching it out, often it doesn't show up. Okay, so that's the basis for ground reaction force during running. Make sure you watch the video showing ground reaction forces from the force platform. Okay, thanks everybody.